Hello and welcome to Physics Tutorials with Oviemine Collins or Nobrakuya. You can simply call me Mr. Collins. In this video we shall be looking at motion on an inclined plane. Alright, in our last video we looked at motion of connected bodies and we were going to talk about motion of connected bodies along inclined planes. However, it's important to first understand the concept of motion on an inclined plane before delving into that one. So I've taken out time to make up this video so that we can first understand this concept before going into motion of connected bodies along inclined planes. Alright, so let us delve into this one, motion on an inclined plane. Let's understand the basics first of all. Let's assume we're given a plane, we're told the body rests on a plane and the plane is inclined at an angle to the horizontal, at an angle theta. Alright, now this is the body in question. It rests on this plane. Now we might be asked to find several things such as the force needed to pull this body up the plane, or its acceleration as it goes up the plane or down the plane. There are several things we might be asked from a question like this. Okay, now it's important to first know all the forces that are at work on this body. Okay, the first force we must consider is its weight. The weight acts vertically downwards, so we can write W equals mg. Of course, where weight is our W here, m stands for mass and g stands for acceleration due to gravity. And then we also would need to know its component, that's the component of the weight parallel to the plane, or the component of the weight perpendicular to the plane. In fact, for most questions, we might need to know both. Okay, some questions will need us to know one, some will need us to know both. So how do we find them? Now, the component which is parallel to the plane can also be drawn along this axis, thus giving us a right angle triangle here. Let's call this O and let's call this B. Let's call this C. So our triangle OBCO is a right angle triangle. Alright? Now, don't forget we're trying to find the expressions for the parallel components and the horizontal, for the parallel components and for the perpendicular components OB. Alright? The parallel is BC while the perpendicular is OB. How do we find them? We must understand what the angle here is so that we can apply our trigonometric identities. Alright, our knowledge of trigonometric identities would help us here. So what therefore is this angle? Now, if you take a look at this triangle here, it is a right angle triangle. Alright, now the sum of the angles in every triangle is 180. So if this is 90 here, it implies that the sum of this angle and this angle must also be 90. And as such, if this is theta, then this should be 90 minus theta. Okay, because the sum of this and this must give us 90 degrees. Now, if we take a look at this line here, we said this is the parallel component while this is the perpendicular component. If you observe, they are at 90 degrees to each other. So if this part here is 90 minus theta, it means therefore that this part here must be theta, because the sum of this angle and this angle must be 90. Alright, so if one side is already 90 minus theta, it implies therefore that this angle must be theta. Okay, now we can apply our trig functions to obtain the parallel component, which is CB, and the perpendicular component, which is OB. Alright, now this right here, our triangle OBCO, looks like a right angle triangle, and of course it is, where its hypotenuse is OC, and then the side which is opposite to the angle is CB. So this is opposite, while our OB is our adjacent side. Now let us apply our trig functions. We know that sine theta is opposite over hypotenuse, which means BC over the weight mg. Alright, don't forget we said that OC here is hypotenuse. Hypotenuse is the opposite, while this is the adjacent. Okay, so it implies therefore that BC is, if we cross multiply here, would have mg sine theta. This implies that the component of the weight that is parallel to the plane is mg sine theta. I could write that here as mg sine theta. Alright, and then the component which is perpendicular to the plane is actually OB. Right, now what connects OB, which is adjacent, with hypotenuse? Of course, if you know your trig functions very well, that will be your cosine. Alright, cos theta, that's the cosine function, is equal to adjacent over hypotenuse, that is OB over the weight, that's mg. And this implies therefore that OB equals mg cos theta, and as such we can say that the component which is perpendicular to the plane is mg cos theta. Okay, now these informations we have just gathered are very useful, as we shall soon see when we solve problems. Now let us take note of something here. Many times this body slides along the plane either downward or upward, but it never experiences a motion into the plane, which means it doesn't crash into it, right? Now, if there is a force that acts downward, that pulls it downward, it therefore means that there must be a force that opposes that downward motion that prevents it from sinking into the plane, alright? And that force is known as the normal reaction, N. Alright, it acts away from the plane, alright, but it is of the same magnitude as our mg cos theta. So it has the same magnitude as our mg cos theta, but it acts in an opposite direction. Thus, it prevents this mass from sinking into the plane. Alright, as such, we could just write that N is equal to mg cos theta. But then I would like to establish a pattern here. So, what is the pattern? Let us use the fact that if we're considering the forces which are perpendicular. So let's just write considering perpendicular forces. Yes, we'll have the net force is equal to the upward one here is N, as a normal reaction, and then the one which acts downward here is our mg cos theta. Now since it acts downward, we give it a negative sign. Alright. Now our net force, as we know from Newton's second law of motion, is equal to ma. Now since the body has no motion perpendicular to the plane, which means it doesn't jump up or sink in, we can say the net force in this axis is 0. Which means we can write 0 in place of our net force equals N minus mg cos theta. And as such, if our mg cos theta is moved to the left, we can write mg cos theta equals our normal reaction. Alright, this expression will be used a lot when we consider the frictional force which acts on the body, bearing in mind that the frictional force is given by Ff equals mu n, which means for such cases we can write it as mu mg cos theta. Alright, now we'll solve questions with this very soon. First question here we have, it says the body which weighs 20,000 Newton rests at the base of a plane inclined at 30 degrees. What is the minimum force required to move the body with constant speed up the plane, given that A, friction is negligible, B, the coefficient of friction between the body and the plane is 0.4 Newton. Let's draw a diagram to depict the question we have in front of us. So this is the body, is inclined at an angle of 30 degrees. Okay, now we have established before now that the component of the weight down the plane is mg sine theta, and the component of the body that is perpendicular to the plane, now this is its weight here, W is equals mg, that's the weight, and then the component of that weight which is perpendicular to the plane is our mg cos theta, where this of course is our theta, which will have been given as 30 degrees. Now let us play with this question. It says, what is the minimum force required to push this body up the plane with a constant acceleration? Now, since we are not considering friction for the question A, we do not need to consider the component which is perpendicular to the plane. Alright, we don't need to consider the component which is perpendicular to the plane. We just consider the ones which are parallel to the plane. As such, we can write that the net force is equal to the force applied, which we have been asked to find, the force applied. Now, we give it a plus sign because it's acting upward, and then minus our mg sine theta, which acts downwards. Our net force is Ma, so we can write Ma equals applied force minus mg sine theta. But then again, we understand that the question says it moves with a constant speed. Alright, if your body travels at a constant speed, it implies that it doesn't undergo acceleration. Acceleration is defined as the change in velocity with time. Alright, so if there's no change in the speed, it implies that there is no acceleration. So we can write 0 equals applied force minus mg sine theta, which implies that if we move this young man here to the left, we can have that mg sine theta is equal to the applied force. As such, the force that we need to apply to move this body up at a constant speed is given by mg, that is the weight, which is 20,000, times sine theta, sine 30. Okay, sine 30 is 0.5. If we multiply that with our 20,000, we'll have 10,000 newtons. So this is the force that we need to apply in order to move this body up the plane at constant speed, neglecting friction. Now, if we have to consider friction, what would our solution be like? Let's do that. If we're considering friction, then we must consider the component of the weight which is perpendicular to the plane. In fact, we must consider all the components of the body, all the components of the forces acting perpendicular to the body, or to the plane rather. So what are these components? Considering the components, or the forces rather, let's put it this way, the forces perpendicular to the plane, to the plane. What do we have now? We can write that our net force, first of all, equals, there is one which goes out, which goes upward, and one which goes downward, right? So we can have N as the upward one minus mg cos theta. Now it's easy for me to just write that N equals mg cos theta, but I'd like for us to have a pattern because we will need this when the question gets more complex. Alright, so our net force, as we all know, is Ma. However, there is no motion of the body perpendicular to the plane. Alright, it doesn't jump up, neither is it compressed inside the plane. So our F net, which is Ma, is equal to 0. because there is no acceleration perpendicular to the plane. Alright, so in place of our F net we can write 0 equals, and then we have n minus mg cos theta. And this implies that n is equal to mg cos theta. I could fix in the angle straight up, but let's not do that. So we'll bring in the formula when the time comes. Now let's consider the forces. Consider the forces which are parallel to the plane. Parallel to the plane. If we do that, what do we have? We can write that the net force is equal to, now there is one which goes upward, that's the applied force, then minus, there is one which goes downward, our mg sine theta. Now we are considering the fact that there is frictional force. Where would friction act? Friction opposes motion, so the force applied pulls the body upward. As such, friction would act downward. It opposes motion, so we can write here minus frictional force. Okay, now don't forget again, we're told that the body travels at constant speed, which implies that our net force is equal to 0. Why? The speed is constant, and as such there is no acceleration, which makes our net force, which is the product of mass and acceleration, to be equal to 0. As such, we can write that 0 equals applied force minus mg sine theta minus our frictional force is given by mu n, where our mu is called the coefficient of friction. Okay, so this implies that if we make our force to be the subject of the formula, we'll have that applied force is equal to, you can move these young men to the left hand side, they would have mg sine theta plus mu n, right? But don't forget we had earlier established that our n is mg cos theta, so we can write mg cos theta, which implies therefore that the applied force is mg into sine theta plus mu cos theta. Let's fix in our values. Our mg is the weight. We're given that the weight is 20,000, right? So we have 20,000 into sine 30 plus our mu, we're told is 0.4 times cos 30. Alright, if you play with this on your calculator, let's see what that will give to us. That would give to us 16.928.2 newtons. Sorry, 16,000, yeah, 16,928.2 newtons. Alright, so we have been able to get the answer to the questions that were given. If you don't get it, you could pause the video or you could play it again until you understand. And if you still don't get it, please let me know on the comments section below. Alright, let's take on another question. Now, it's important to go through these steps to get a full knowledge of this topic. As we go on from one question to the other, the level of difficulty of the questions increase. So don't just stop at one question, ensure you go through it to the end of the video. Alright, now let us take out a second question. So this one says a body which weighs 20,000 newtons rests at the base of a plane inclined at 30 degrees to the horizontal. If a force is applied to increase its speed gradually as it is moved up the incline, what energy will produce a force that will give the body a speed of 15 meters per second after 5 seconds? Okay, so this one is not moving at a constant speed, but its speed builds up over time, okay, such that at 5 seconds its speed is 15 meters per second. So we're told to find the energy that would produce a force that will give it that speed. A, if the effect of friction is negligible, and B, if the coefficient of friction between the body and the plane is 0.4. Alright, now please don't forget that the coefficient of friction has no unit. Alright, so let us solve this question. Again, we can draw a plane just to be able to properly conceptualize the question we have in front of us. Okay, so the plane is inclined at 30 degrees to the horizontal, and this is the body which has a weight of 20,000 newtons. Alright, now we are told it accelerates. How do we know that? We're told it was first at rest, and then it moves gradually, it increases its speed gradually. Okay, so we must first find the value of its acceleration. Okay, it means we need to apply the equations of motion, and the most ideal one for this one would be v equals u plus at, where v is the final velocity, u is its initial velocity, a is acceleration, and t represents the time. Alright, now we're trying to find the acceleration here. Okay, now our v here, we're told it's 15, right? It starts from rest, so u is 0. Its acceleration is what we seek to find, that's a, and then the time is 5 seconds. So let's fix in the values. We would have 15 equals 0 plus a times 5, alright? Which implies that 15 equals 5a. If we write both sides by 5, we'll have that the acceleration of the system is 15 over 5, and that gives us 3 meters per second squared. Alright, having done that, let's now go ahead to find the force. Now, don't forget the question says find the energy, but we know that energy is the product of force and displacement. Alright, so let us first find the force, and then we'll also need to find the displacement at some point. So probably we should just do that first. Okay, we can also use another expression, another equation of motion, S equals ut plus half at squared. Alright, now again, since it starts from rest, u is 0, which implies that S is equal to half at squared. That's half times our a is 3, and the t is 5, so the square of 5. Alright, now half times 3 is 1.5. 1.5 times 5 squared should give us 37.5, so we have 37.5 meters. Alright, so we have found the acceleration, we have found the displacement S. Let us find the force so that we can get the energy. Alright, now the force will need us to find several things. First of all, we know that the weight acts vertically downwards. Alright, the weight is equal to mg. Then it has two components, a component which is parallel to the plane, that's mg sine theta, and a component which is perpendicular to the plane, that's mg cos theta. Of course, here our theta is 30 degrees. Alright, so how do we find the force? Let us first consider, now for the A part, A here says neglecting friction, right? So we can write that the net force. Now, since we do not need to consider friction, it means we do not need to consider the perpendicular component of the forces acting on the body. Alright, we will only concern ourselves with the parallel component, which is our mg sine theta, which acts downward, and the applied force, which pulls it upward. Okay, so we'll have that the net force therefore becomes equal to the applied force, which acts upward, minus the mg sine theta, which is the weight, that's a component of the weight which seeks to pull it down the plane. Alright, now our net force is equal to ma, so we can write ma equals F minus mg sine theta. Alright, which means that the applied force therefore becomes equal to ma plus mg sine theta. Factorize, we'll have m into a plus g sine theta. Alright, now m, we do not know m, but we know that the weight is equal to mg, right? And now we're told that we're told to take our g as 10 meters per second squared there, which implies that the mass therefore becomes equal to the weight over g, that's 20,000 over 10, which we're given, and that gives us 2,000, right? 2,000 kilograms. So let's put that now in this expression. As such, we have that the force is equal to 2,000 into a. We found a to be 3, so 3 plus our g. We're told to take g as 10, so we have 10 sine 30. If you pull this together, if you punch your calculator, you will get the value as 16,000. So 16,000 newtons. Alright, that's the force that we'll need to apply if there is no frictional force. However, if there is friction to be considered, then the story will change. Now let's not forget something here. We're told to find the energy, not the force. Interesting. I almost forgot that one. So the energy, like we said earlier, is equal to the product of force and displacement. So we can write 16,000 times the displacement, which we found to be 37.5 meters. We play with that, we would have 600,000 joules. 600,000 joules, which is like writing 600 kilojoules. Alright, now let us go to the B part. The B part says, let's assume that there is frictional force. What will the story be like? Okay, now in this one we must consider the components of the forces which are perpendicular to the plane. Alright, now we have said the normal reaction M, which acts upward, is equal to our mg cos theta because it balances it or it cancels it out. Alright, I could go through the long route of writing F net equals n minus mg cos theta and all that, but that will be stultifying. So let's just go straight to writing mg cos theta. Now, there are cases we will solve where we would see that this will no more hold, but we will solve that. Alright, we'll solve such cases. Just be patient, we'll get there. So n equals mg cos theta. This assumption is safe for now. Okay, and as such, this is the components. Let's call this equation 1. This is for the components which are perpendicular to the plane. Alright, now let us consider the components which are parallel to the plane. For such ones, we can have F net equals the force applied, which takes it upward, minus mg sine theta, which is the component of the weight that pulls it down. And then now we are considering friction, right? Now friction opposes motion. Since the force pulls it upward, it means friction would act backward against the motion of the body. Alright, so we can write that F net equals F, which is upward, minus mg sine theta, which is downward, and then minus frictional force. Okay, because friction acts downward in this case. Alright, if this body were to be going downward, for instance, then our friction would be acting upward. Alright, so let's come back to this case that we have in front of us. Our net force is MA. We have MA equals applied force minus mg sine theta minus our frictional force is mu n, but our n is mg cos theta, so we can write mu mg cos theta. If we make our F, the force applied, the subject of the formula, we would have ma plus mg sine theta plus mu mg cos theta. Don't forget that mu here stands for the coefficient of friction. Alright, so we can factorize our m and our g to have something like this, m into a plus. Now, if we check out these two parts, we would see that our g and g is common in both terms. Okay, we've already factorized out m, so the common thing amongst these two terms is g. I can factorize that out to have g into left with sine theta plus mu cos theta. Now, you could also solve this. You could impute the values here without factorizing. Alright? If this looks a bit confusing, you can just go ahead and fix in your values here and you'd still be correct. Alright? So let's fix in our values now. We can have 2000 kilograms, which is the mass, into 3 plus, we're told to take g as 10, so we have 10 into sine 30 plus 0.4 cos 30. You play with this, you put these together, and you would have a value of 22,928.2 newtons. Alright, but don't forget the question didn't say find the energy. The question didn't say find the force, it said find the energy. So our energy is equal to force times displacement, and so we'd have 22,928.2 times the displacement, which we found to be 37.5, right? So we have 37.5. You put that together and you would have a value of 859,807.5 joules. That's approximately 860 kilojoules. So this is the energy that would be expended if there is friction. You can compare both energies and see that would spend more energy in trying to overcome friction than we would if there were no friction at all. Alright? So let's wrap up the topic with this question. It says, a mechanical device which has a horizontally pointed arm is used to push a 5,000 kg body up a plane inclined at 30 degrees to the horizontal. It says calculate the force that is required to give the body an acceleration of 0.75 meters per second squared, given that the coefficient of friction between the body and the plane is 0.4. We're told here to take g, that is acceleration due to gravity, as 9.8 meters per second squared. So let's conceptualize the problem. It's supposed to be a straight line, okay? And then we have 30 degrees here. We have the body here. This is our 5,000 kg body. Now we are told that the device has an arm which points out horizontally. Okay? It means the force it applies would act in the horizontal direction. So this is the applied force. Okay? Now this force has two components. It has a component which is parallel to the plane and a component which is perpendicular to the plane. Okay? Now these things will come in handy as we solve this question. Okay? Now let us first find all the components of the forces which are perpendicular to the plane. Don't forget we have the component of the weight, mg sine theta. This itself is the weight. It acts vertically downwards. W equals mg. And then there's also a component which is perpendicular to the plane, the component of the weight. That's mg cos theta. So let us consider the perpendicular forces. We are doing this because friction is involved here. Okay, so we can write F net equals, now of course we know that there's a normal reaction here which goes out of the body. It acts outward, alright, in the opposite direction to mg cos theta. Now we must also resolve something here, the applied force. Okay, the applied force acts horizontally. Like I said earlier, there's a component that is parallel to the plane and a component perpendicular, such that the angle here is at 30 degrees. Let's just call it theta. Okay, now how do we get the expressions for the parallel and the perpendicular component? If this is theta, we can also draw this we can draw this perpendicular components again on this side. Let me just draw it out here. This is the force applied. This is the perpendicular components, and then this is the parallel components. The angle between them, of course, is 90, but the angle between this component and F is at 30 degrees. We can redraw this components here such that it's at 90 degrees to the component which is parallel to the plane. Alright, so this is similar to this. The vectors are the same because they have the same magnitude and they are acting in the same direction. Okay, now this here is a right angle triangle. This F here is the magnitude of its hypotenuse, and this axis here, if we call this OAB, the axis AB gives us the opposites because that is the side that faces the angle theta. What trigonometric function connects hypotenuse with opposites? It's a sine function, of course, which implies that our side AB can be expressed as F sine theta. Alright, while the component here which is parallel to the plane, that's this one here, is the cosine, or is linked to the force F by the cosine function, which means this component here is F cos theta. Alright, don't forget your sine is opposite over hypotenuse, while the cosine is adjacent, that's our OA over hypotenuse. Alright, with that in mind, you would have your F sine theta as AB and F cos theta as OA. So let us write them out here. The component of the force applied, which is parallel to the plane, is F cos theta, while the component which is at 90 degrees to the plane, which is perpendicular to the plane, is F sine theta. Okay, so let's apply that now. We are considering the perpendicular forces, right? Which means we have F net equals, now which one acts upward? It's our N. And then we have our mg cos theta acting downward, so we give it a minus sign. And then there's also a component of the force which acts downward as well. Alright, that's F sine theta, so we write minus F sine theta. Alright, now there is no motion of the body along that axis. Alright, as such, our F net, which is equal to MA, is equal to 0 when we are considering the forces which are perpendicular to the plane. Alright, so we have 0 equals N minus mg cos theta minus F sine theta, and as such we can write that N equals mg cos theta plus F sine theta. We can call this equation 1. We'll apply that later. Now let us consider the forces which are parallel to the plane. Considering parallel forces. Now, I would challenge you at this point to pause the video and then write out the expression for the forces. Okay? If you have done that, then let us check out what it should be. We have F net, the applied force, the net force rather, is equal to, now, which of the components of the forces move upward? It should have just been the force, right? But our force acts horizontally, right? So the component which is parallel to the plane is F cos theta. So we should write F cos theta. And then which are the forces that act downward? One is the component of its weight, right? So we write minus mg sine theta. And we're told to consider friction in this question. Now, if the force pulls it upward, friction would act in the downward direction. Alright, so minus frictional force. Okay, now we have MA. Now, this is not going to be equal to 0 because we're told that the body has an acceleration as it moves up along the plane. Alright, so we have MA equals F cos theta. Now, if you study the case for the perpendicular forces, we didn't use this value of A that was given to us, alright, because that acceleration was used to take the body up the incline, which means it acted parallel to the plane. Okay, so that is why we are considering it only when we're considering the parallel forces. Alright, so let's go to the question. We have MA equals F cos theta minus mg sine theta. Then our frictional force is mu n, right? So mu, but don't forget, now please, this is mu, not n in itself. Now this is mu. Now don't forget we said that n is mg cos theta plus f sine theta, right? So let's put that here. We'll have mg cos theta plus f sine theta. Okay, so let us express this further. We have f cos theta. Let's open up our bracket. Minus mg sine theta minus mu mg cos theta minus mu f sine theta. Alright, now let us collect like terms. We'll have ma. Let's move all the terms without force to one side. So we'll have minus mu mg, sorry, this will become a plus mu mg cos theta, and then plus mg sine theta. So our ma is still here. Our mg cos theta, mu mg cos theta moved down to this side, it became a plus. Now mg sine theta also moved over to this side, it became a plus, equals, we're left with f cos theta and mu f sine theta. Let us factorize out f. We'll have f into cos theta minus mu sine theta. Okay, so from there we'll have f equals, I could factorize this or just write them the same way. Whichever way you would still get your answer. I could write it out as m into, now because m is here, here and here, right? M into a plus, again our g is common, so we can bring out g. Then we'll have mu cos theta plus sine theta. Alright, and then divided by the coefficient of f here, which is cos theta minus mu sine theta. Alright, at this point we can fix in our values. Have f equals, we're told that the mass is 5,000 kg into the acceleration is 0.75 plus, we're told our g is 9.8 for this question, our mu is 0.4 cos 30 plus sine 30 over cos 30 minus 0.4 sine 30. Alright, I'll bring the final answer up here for the sake of space. We'll have that the force applied, if you punch your calculator, the force applied is 67,901.449 newtons, which is approximately 68,000 newtons. Alright, so if you have enjoyed this video, give it a thumbs up, like it, that's click the like button, and then subscribe so that you'll be notified when subsequent videos are released. Now that we have treated the motion of bodies along inclined planes, we can now go on to talk about motion of connected bodies along inclined planes. Alright, it's important to go step by step so that we are not confused. Alright, so thanks to all my subscribers from different parts of the world. I can see some of us from Ghana, some from India, from the UK, the US, and so on and so forth, and from Nigeria. So thank you for following. Please, if you have suggestions, if you have contributions, if you have questions or topics in physics you would like for me to treat, let me know on the comment section and I'll do justice to the questions or to the topics. Alright, so see you in our next video. Thanks for watching.